Hi, welcome to es346 Basic Thermodynamics. I'm Rourke Peterson. This is the first module, module 1.1. The topic is what is thermodynamics. The corresponding section in the textbook is section 1.1 of Single and Bold. Alright, let me just show here or discuss the course outline for this class. There's 4 bullet items I have here. And the first thing is an introduction and background. And the corresponding chapters are 1 and 2 of the book. This is a lot of definitions of thermodynamics and some background in the important physics and calculus that you'll need to know for this class. Then in chapter 3, we'll mention fluid properties. After those first 3 chapters, we'll have our first exam. Then we'll move on to the first law of thermodynamics. It's covered in chapters 4 and 5. We'll discuss closed systems, open systems, and unsteady systems. And after that, we'll have the second exam. Then we'll move into the third section of the course, where we'll discuss the second law of thermodynamics. It's covered in chapters 6, 7, and 8, and we'll talk about concepts like the Carnot cycle, entropy, and exergy. And then we'll wrap up with the third exam. Okay, so let's discuss what's the learning objective of this module, and there's one objective. I simply want to do is define what is thermodynamics. So, first off with a little bit of background. The word thermodynamics comes from 2 Latin words, thermae and dynamis, which means heat and power. Early thermodynamicists were interested in turning heat into power. That was an energy transformation. And that was what spurred them to doing what is now known as the study of thermodynamics. So, there's 2 basic laws that are important that we will cover in this class. And the first, known as the first law of thermodynamics, deals with energy conservation. It says that the amount of energy in the universe is constant. It can change forms, but the total sum of all the energy never changes. The second concept, which is dealt with the second law of thermodynamics, says that energy has quality. If you think back to this first bullet item over here where I mentioned early thermodynamicists were interested in turning heat into power, well, it turns out that heat is disorganized energy, power is organized energy. And this transformation of going from heat to power can only be done with a certain efficiency. And we'll look, if we do the transformation from an organized energy back to a disorganized energy, we can do that with a much higher efficiency. All right, let's look at just a couple systems and talk about how thermodynamics applies to them. Here I show a regular household refrigerator. And if we think about what types of energy transformations are occurring in here, well, the first one might be obvious, is that there's probably a power cord that this refrigerator is plugged into the wall. And it's just consuming power. So I'm going to go ahead and give that the symbol W with a dot over it. I'm going to use W because electricity is a form of work, and the dot will just represent that this is occurring over time, a rate. Electricity is going into this system and going into this refrigerator. Now, if you ever felt the back of the refrigerator, you probably saw there were some warm coils, and they were losing heat, dissipating heat, off of the refrigerator. I'm going to call that energy Q, and that Q comes from caloric. Now, there's another energy transfer occurring here that may or may not be obvious. Since the inside of the refrigerator is colder than the outside, there is heat that is diffusing from inside the room into the refrigerator. It is being conducted through the walls and every time we open the door. So therefore, we have 3 energy transfers going on here. The first law describes how they are all conserved, and the second law describes how well one gets transferred into another. All right, here's another thermodynamic system. I have a well pump here. It is bringing a fluid up from below ground, water, or probably this looks like an oil pump. And so here I've got an energy transformation. It is changing potential energy into, it is transferring electrical energy into potential energy. I'm trying to increase the potential energy of the fluid, bringing it from below ground up ground. And in order to increase the potential energy of the fluid, the energy comes from, powered from this pump. It might be electrical energy, or we also see we've got an oil fuel tank over here, another fuel tank, so maybe this is being powered by a generator that is turning chemical energy into electrical energy and then ultimately into potential energy. Here's another thermodynamic system. We've got a series of wind turbines, and the energy transformation going on here is they're taking the kinetic energy of the wind and converting it into electrical energy that powers the grid. And in fact, inside each one of these turbines is a generator that has a certain efficiency. So here we see first law of thermodynamics, where kinetic energy is turned into electrical energy, and we see the second law in the efficiencies of the generators on each turbine. All right, here's one final example. This is sort of the classic thermodynamic example, and what we have here is a power plant. And there's a lot of energy transformations going on here. First, this power plant needs to be powered by some type of fuel. Maybe it's coal or natural gas. And so the energy is coming in the form of chemical energy of that fuel. That is then being burned, so it is then turning into thermal energy. And then that thermal energy is being fed through a series of turbines and generators into electrical power. So here we realize we've got two energy transformations, chemical to thermal, thermal to power, and each one of those can happen with a certain efficiency. So now we can return to this initial question of what is thermodynamics? Well, thermodynamics describes energy transformations, and it does it through the first law, and thermodynamics also describes the efficiency of those transformations, and it does it through the second law.